Hello and welcome to our glider project for AE 1601. I'm Calvin Tomsic and my partner was Alfonso Lagares de Toledo. So the outline for this presentation is going to be as follows. First, we're going to consider the design process. We're going to start with what are the requirements for this project, what were some of the alternative design choices that we had, and what was the initial concept that we eventually went with. What was our initial testing and the results from that. Next, what were some iterations of our design? What changes did we make before the final flight test, which is the next section? And then we're going to finish off with an overall summary. Based on the given vehicle requirements for this assignment, we produced the following list separated into material constraints, design constraints, and mission constraints. Our measure of success for our requirements was to fulfill the mission constraints and to fall within the rules of the competition. We were limited in materials to the provided balsa and wood dowel, and by the competition rules on our design. Traveling as far as possible in each flight without damage to the glider was our primary measure of success. Our two design sketches on the left show some alternative design choices that we could have made. The four main design choices that we considered in this project were the inclusion of a dihedral angle and the angle of attack on the fixed wing, the wing's plan form, and the adhesive used in manufacturing. These considerations also had to do with the stability of the vehicle, ease of manufacturing, its durability, and the vehicle's lift and drag. While we found research on an ideal dihedral angle for gliders of around 5 degrees that is in our references at the end, that would ideally increase the stability of the aircraft, but we decided against the dihedral due to its more complex manufacturing and to increase the durability of the wing component. Using research on lift coefficients of glider aircraft, which is also in our references, we attempted to manufacture an angle of attack of 5 degrees to increase our lift, but the actual angle of attack we got is about 3 degrees. Based on our research on wing planforms, again in our references, we decided to use a rounded middle taper on our design instead of a rectangular wing, or the rectangular taper that you see in our first design here on the left, to increase our lift to drag ratio, limit tip vortices, and increase the aircraft stability without significantly increasing the manufacturing complexity. Finally, we decided to use balsa wood glue instead of normal wood glue to better penetrate the material to create a durable composite, as well as tape for repair during the flight competition in case there was a rapid unscheduled disassembly. The dimensions listed on the left were chosen based on in-class lecture notes, research on balsa wood glider aspect ratios found in our references, and maximizing the wingspan within the design requirements in order to increase our aspect ratio and improve our flight efficiency. To calculate an estimation for the coefficient of lift, we use the thin wing formula from the in-class lecture on aerodynamics. This is the set of equations on the bottom left that state CL is approximately 2 pi alpha. Using our 3 degrees angle of attack, we estimated coefficient of lift to be 0.3289. To calculate an estimation for the coefficient of drag, we use the equation for induced drag, CDI, given in the aerodynamics lecture, as well as an equation for parasitic drag, CD0, from synthesis of subsonic airplane design in our references. This estimation idealizes our flight as steady level flight, which would mean our lift is equal to our weight, and allows us to calculate the induced drag coefficient as 0.00198, using our coefficient of lift and the parasitic drag equation, as shown on the bottom right, and using a table of standard values from the synthesis of airplane design, we again estimate our glider's parasitic drag to be 0.060, bringing our total coefficient of drag to 0.0612.
This is our initial glider concept. Its design was driven by the project's requirements. Material constraints drove our decision to choose easy to manufacture dihedral and angle of attack values, as well as our adhesive choice. Following design constraints, we chose a wing platform that increased stability and reduced drag in order to maximize range and survivability, in order to fulfill our mission requirements. Our design fits in a 16 by 16 inch bounding box, as shown by the image, and its center of gravity ended up falling on the quarter chord of the wing when balancing weight was added. During initial testing, we determined that adding 55 grams to the nose cone of the glider was ideal to ensure longitudinal stability and allowed for a level flight. We found that the glider had a slight tendency to deviate left, probably due to some manufacturing mistakes. Most likely the wing was not mounted perfectly perpendicular to the body, and so we had more induced drag on one side of the vehicle, which caused it to veer off course. We completed a total of 3 flight tests, with the maximum being 25 feet, as shown in the video. Sadly, we discovered this vehicle suffered of poor durability due to delamination issues with the balsa wood in the wings, and we suffered an unscheduled disassembly on the 3rd flight test, which meant that this design would fail to meet requirements. After initial testing, we made a number of changes to improve our glider design. These were mainly manufacturing changes, as we determined most of the issues with our initial design stemmed from how it was manufactured. We laser cut new wings, which gave us cleaner edges and lowered our delamination risk. We also reinforced the wing edges with super glue to reduce the chances that a wing strike while landing would damage the wing beyond repair. Finally, we added small balsa reinforcements to both the wingtips and wing core, which ensured the glider would survive flight while only sustaining repairable damage. After manufacturing our second glider design and testing it, we decided to present it at the flight test competition. On our first flight, the glider managed to achieve a distance of 33 feet. On our second flight, the glider managed to achieve a distance of 31 feet, which put us through to the second phase of the competition. On the third flight, the glider achieved a distance of 61 feet, and on the fourth flight, the glider achieved a distance of 63 feet, which was our best flight ever recorded on this design. This put us on the top 4 of the class, and after competing in that 5th flight, we managed to achieve a distance of 55 feet and placed on the 4th place for the entire class. In summary, our glider effectively fulfilled the project's requirements, and we persevered as a group after a failed initial design. We're especially proud at the consistency and reliability of our design during the final competition, as it averaged very high range throughout the entire competition. However, we felt like our design was a bit too conservative. If we had to do this all over again, we could have taken more risks at the beginning of the design process in order to improve our final range. Finally, these are the references that have been shown in previous slides.